Welcome. We are looking into preconditioning technologies, preconditioning techniques I should say, and we have looked into how preconditioned conjugate gradient can be obtained, or for symmetric matrices how preconditioners can be obtained, so that the preconditioned matrix also remained a symmetric positive definite one, and looked into two different variants of conjugate gradient, the split preconditioned conjugate gradient and the left preconditioned conjugate gradient. We have not discussed in detail how the preconditioner matrix is obtained till now, but we have seen that different algorithm, slightly different from the original algorithm, can be proposed if we think of a preconditioned system of equations, where the inverse, the preconditioned matrix M inverse or part of the preconditioned matrix L inverse transpose are already available with us, how these algorithms will look like. But now we will see for general matrices where we cannot apply conjugate gradient, which are non-symmetric matrices, where still we can apply a Krylov space method like GMRES, the preconditioning can be done. So, we start with left preconditioning of GMRES. The left preconditioned system M inverse x is equal to M inverse b. Now, instead of solving x is equal to b, if we are solving M inverse x is equal to M inverse b for GMRES, as we have to evaluate the basis vectors of the Krylov subspace K M, we will find out the Krylov subspace for R naught M inverse R naught M inverse A R naught. Instead of finding R naught M inverse A R naught M inverse A M minus R naught. So, instead of finding K M, this will be K M of M inverse A R naught. For x is equal to b, we use the Krylov subspace of A R naught. Now, as we are solving M inverse A x is equal to b, we will use Krylov subspace of M inverse A R naught. So, this will be an M inverse A R naught up to M inverse A to the power m minus 1 R naught. The Krylov subspace will change, and we will use something like a Arnoldi modified Gram-Schmidt to obtain the basis vectors for the Krylov subspace of this, for this particular Krylov subspace. All the residue vectors and their norms will be found using the preconditioned residual z is equal to M inverse b minus a x. So, the Krylov subspace vectors are found for A, the Krylov subspace vector are found for M inverse A and R naught, and the residue vector Z, where the new residue vector rather R naught is equal to M inverse b minus a x 0. This is the new residue vector, and that is how. So, instead of solving x is equal to b, we are solving M inverse x is equal to b in a GMRES. There is no other change, only the idea is that solving M inverse x is equal to b. So, wherever we have A will be replaced by M inverse, and initial R naught finding is that, then the orthogonalization step will require finding W, which was in GMRES finding A V j. Once V is on one of the basis of the Krylov subspace, we are orthonormalizing the other bases, W will be M inverse A V j, and it will follow the Arnoldi Gram-Schmidt type of steps, and then we will compute the the elements of the Heisenberg matrix H, which is L2 matrix of W, and then using the L2 norm of W will normalize the V j. So that it becomes the set becomes an orthonormal set, and we will define the V m matrix H m. Finally, Y m will be obtained by a minimization of beta E 1 minus H bar m y. These algorithms we have looked earlier. This is very similar as Jacobi algorithm, and x m will be updated such that, and once we are satisfied, then stop, otherwise you update the gauge value x 0 with x m and continue with this loop. So, this is nothing but modifying the GMRES, considering that we, instead of solving x is equal to b, we are solving M inverse x is equal to b. While doing so, we get two important steps here. One is M inverse, first M inverse b minus x 0, which is one time step at least which you have to do ever. So, M inverse not one time step, at every iteration you have to do. So, at every and also M inverse A B 0. So, every iteration requires a evaluation of the matrix M inverse or of the preconditioned matrix M inverse. So, it is very similar to conjugate gradient method. The problem is very similar to conjugate gradient method. In conjugate gradient method, we had the requirement of finding M inverse or L inverse transpose and multiplying it with certain vector for preconditioning. Here also you have the requirement in the preconditioned steps itself. So, this can be thought of a finding M inverse A matrix and this can be thought of finding M inverse. So, two operations are there actually. Right preconditioned conjugate gradient, we have A M inverse U is equal to B and U is equal to M x. The Krylov subspace is now of A M inverse instead of A inverse. So, A it is R 0 A M inverse R 0 A M inverse, this A is not here, A M inverse A m to the power minus 1 R 0. So, this is called Krylov subspace. We have to find out K m of A m inverse and R 0, and R 0 is the residual of this particular matrix system. R 0 is equal to B minus A x 0, which is B minus A m inverse A u 0. The initial residual is this. Now, once we get all the basis of Krylov subspace and the corresponding weights eta I. So, we can find out the final solution of this equation of A m in rather we will find we have the equation A m inverse u is equal to B. So, once we find out all the basis of the Krylov subspace of A m inverse and the corresponding weights to get the final solution, we can write u m is equal to u 0 plus the basis into certain coefficient on that. So, the final solution will be u 0 will be in an affine subspace of the affine Krylov subspace, which is u 0 plus this vector, and V i's are the basis of Krylov subspace of u m of A m inverse and R. So, this is V i's are the basis of Krylov subspace and eta I are the weight, which is eta I are the elements of the vector y m, which are obtained after minimization of beta e 1 minus h bar m. This will give that x m. So, x is equal to, we also know that x is equal to m inverse u. So, we will multiply m inverse here and we will get x. X m is equal to x 0 plus m inverse V I y eta I. So, once we get the weights eta I, which are the elements of the vector y m, and the basis of Krylov subspaces are formed, we can directly find out x m without evaluating u. So, the algorithm will become x m is equal to x 0 plus m inverse V m y m. The original algorithm was x m is equal to x 0 plus V m y m, here it will be x 0 plus m inverse V m y m. Important thing is that we again have to go into a matrix inversion or a matrix solution of M inverse. We again have to find out M inverse here, we are stuck with the same problem. Another important observation is that exactly same as our old method, last discussed method, which is split preconditioned conjugate gradient, or if we think of right preconditioned conjugate gradient, we do not have need to, we did not need to evaluate u there. Here also we do not need to explicitly evaluate u, rather we can directly find out x if we have find out the basis vectors of the Krylov subspace A m inverse and R. The algorithm does not need explicit evaluation of u vector, x m can be directly computed using this. So, look into the right preconditioned GMRES algorithm. It starts with the initial steps, and now the basis vectors of V is computed by A m inverse. So, an M inverse step is needed and remaining all the steps are exactly same as the original GMRES, except while finding M x m we need M inverse. So, these two operators are required, M inverse and M inverse. So, we are kind of every time encountering the same problem that the preconditioned equation look very similar to the preconditioned algorithm, look very similar to the older algorithm, only we have to find the operators where M inverse is included or the preconditioning matrix is included. So, how will we find preconditioned matrix? That becomes the important question here. However, we have demonstrated that different preconditioned algorithms can be obtained for both conjugate gradient and GMRES, and the algorithms are very similar to the older algorithm. So, if we already have a code, we can with very less effort we can convert it to a preconditioned code. Only thing, this M inverse and M inverse are to be found out. Now, one question is that if M inverse is very close to identity, the problem becomes much simple and the condition numbers also improve, because identity matrix has a condition number 1. So, condition number also improves and we get faster solution. So, how can we find out M inverse which is very close to A? That is one important thing. Another thing, because we need to do M inverse in certain calculations, not M inverse. M inverse is one issue, M inverse is another issue. These two things have to look in, that we have to find out an M inverse or M inverse say for the left preconditioned GMRES or for conjugate gradient, which has a good condition number. So, if M is close to A, the condition number will be close to 1 and the solution will converge faster. So, this is one issue, that M should be very close to A, so that M inverse or M inverse A is close to 1. The other issue is that M inverse is to be evaluated in a form, so that this equation can be well solved. And we will see, we already have some idea that M is of LU. If M is of LU form, the solution of M inverse equation involving M inverse is much simpler. All the preconditioning techniques show nearly same convergence pattern if M is not ill conditioned, for left, right, split preconditioning, all these things. Split preconditioning may help where A is nearly symmetric. To calculate W during Arnoldi steps, left preconditioners use inverse matrix M inverse A and right preconditioner use A M inverse. So, this is important, that if M inverse is close to A, M is close to A, M inverse is close to A inverse, this will be identity and we will get very fast the convergence of this method. It is useful to calculate an M which is nearly equal to A. If M is equal to LU, M should be close to LU factorization of A. There is another method called flexible preconditioner, where the preconditioner can change in every iteration. Instead of going with a fixed M, I can change M at different steps, so that the action M j inverse on vector V of Krylov space is now no longer applied to the entire span of V m j plus 1, because M j inverse is calculated at one particular step of the iteration. So, its in application, it is not applied over the entire Krylov subspace of vectors. Rather, the solution is obtained as x m is equal to x 0 plus y m z m, and the z m, the column vectors of J, is found out as M j inverse V j. So, it uses only one particular Krylov subspace vector and the preconditioner used at that particular step, which gives z m is equal to V m plus 1 h bar m. Y m is obtained as the minimizer of beta E 1 minus h bar m, like any standard GMRES method. Now comes the issue that how the preconditioners can be chosen. It may be good to obtain a symmetric preconditioner, especially when A matrix is symmetric or near symmetric. A preconditioner like MALL transpose will be of use. We have seen that from our idea discussion in conjugate gradient method. As M inverse and M inverse A are often to be computed, a preconditioner matrix M which is nearly equal to A is often sought for, because M inverse and M inverse A will be close to identity there, and that is the driving part of the algorithm, because we find out Krylov subspace of M inverse and M inverse A and the residual If this is close to identity, the problem becomes much simple. This is straightforward. This further necessitates having LU transformation of A as preconditioner, because we need some sort of LU transformation of to get M inverse. M inverse will be an LU, and M inverse and M inverse A will be close to identity. So, a LU transformation of A, if it is obtained, that can be the best preconditioner, and we can see if M is equal to A of LU, or that means M inverse is basically A inverse, the problem becomes an solution of an identity matrix and should be done in one step. So, even if we cannot get exact LU transformation of U because LU transformation is a costly operation, we should try to get a near LU transformation of A. The preconditioner may change at different iteration levels, which we have seen from flexible GMRES. So, at different iteration levels we can try to recompute the preconditioner, which is also possible if we are using flexible GMRES. It might be well avoided to explicitly evaluate the precondition matrix M. Rather, the operators M inverse and M inverse at different stages and how are the effect of the operators in the solution, that can be computed. So, instead of computing the M, evaluating the M, storing it somewhere, we should rather see how is the matrix product of M inverse into something or M inverse into something can be directly used. So, now we will look into few preconditioning methods, and one is called a Jacobi type preconditioner, and that is that we will look into how M can be evaluated using Jacobi or SOR iterations. Can they be used as preconditioner? The general form of an iterative step is mxk plus 1 is equal to nxk plus b, which is m minus a xk plus b. For Jacobi, M is equal to the diagonal matrix, n is minus e minus f. For Gauss Seidel, M is equal to d minus e, n is equal to minus f. So, D is split into upper triangular, the matrix A is split into diagonal, upper triangular and lower triangular matrix. This we have done in when long back when we were discussing about basic iterative methods. And iteration step is written as xk plus 1 is equal to gxk plus f. G, which is equal to M inverse n, is called the iteration matrix, and f is equal to M inverse b. If the iteration converges, we get x at the converging step, we will get x is equal to gx plus f, or the equation will be I minus gx is equal to f, which is same as if we look into this splitting, M inverse Ax is equal to M inverse b. So, we got it that converging Jacobi or Gauss Seidel iteration gives us exactly same what we are looking for as a preconditioned system of equation. So, if instead of solving x is equal to b, if we can do few Jacobi iterates and get a M inverse x is equal to b, which will be already a preconditioned system of equation and will probably have faster convergence. The other thing is that how will M inverse look here, and especially if we can have a LU decomposed form of M inverse, or also you can see whether M inverse is close to A. If M inverse is same as A, this is x is equal to A inverse b, we have already arrived at the solution. So, that we will also look into, but this equation is already a preconditioned equation, which is the converging step of Jacobi iteration or Gauss Seidel iteration. So, as we use Gauss Seidel or Jacobi iterates, we are actually preconditioning the equation system. The above equation is the preconditioned form of x is equal to b. Hence, Krylov space solvers can be used to solve this equation. So, one very smart, very quick approach will be do few Jacobi or Gauss Seidel iterations, get something like an M inverse x is equal to M inverse b. This M inverse is not exactly same, this is as your I minus g M inverse a, because unless convergence you have not reached into x is equal to gx plus f, but this will be close to that. So, this will be a preconditioned system and solve it using Krylov space solvers. So, the matrix M inverse obtained through Jacobi or GS iteration can be chosen as the preconditioner, and that is another idea, that M inverse, that which is the Jacobi iteration matrix I minus G matrix, that can be chosen as a preconditioner and can be applied in the Krylov space based solvers conjugate gradient or GMRES. This M inverse, which is I minus G, can be taken and applied there. Now, we have to see whether this is symmetric also, because symmetricity is required in some cases. A symmetric method can be thought of symmetric successive over relaxation steps. We have discussed about successive over relaxation, but this is successive over relaxation combining two steps. One is combining the lower triangular already updated part of the vectors, and another if updating the other elements of the vector, and then getting the final update using this updates here. So, this is the SOR is broken into two half steps, which is called symmetric preconditioning. If W is equal to 1, this gives us symmetric Gauss-Seidel or SGS step, and the matrix M obtained from SGS is D minus E D inverse D minus F. If we look into the M matrix, the M inverse A, that M matrix A is equal to M minus N, the M matrix obtained from SGS is D minus E D minus E, which is a lower triangular matrix. D is a diagonal. So, D inverse is a diagonal. So, this is a lower triangular into D minus F, which is an upper triangular matrix. So, MSGS, if we use symmetric Gauss-Seidel, that is symmetric successive over relaxation with omega is equal to 1, we get an M matrix which is of LU form. L is equal to D minus E D inverse, which is I minus E D inverse, U is equal to D minus F. Now, if we have to find out Z is equal to M inverse V, some M inverse operation has to be done. The first operation will be I minus, because this is LU. So, L W is equal to V, which is I minus E D inverse W is equal to V, and because this is lower triangular matrix, there will be exactly n steps to solve this equation, and the next step will be the U part D minus F Z is equal to W, which will give us, this is upper triangular, this will be again n steps. So, very quickly we can get solution of Z is equal to M inverse V if we have the MSGS form, the LU decomposition through SGS preconditioning. The operator M inverse A will be computed through the SGS iteration steps, M is equal to LU, and then if we write, so this will be that means that as we will do some of the SGS iterations, we are actually using applying the operator M inverse A. We do not need to explicitly find out M inverse and multiply it with A. Some of the SGS preconditioning steps will take care of M inverse A operation multiplication, or the operator is already updated. Now, this M inverse is not exactly M inverse. So, if we find out MSGS and A minus LU, this is LU, A minus LU, we get a solution which is ED minus ED inverse F. So, this is the error in the LU decomposition. The LU decomposition of M is not same as LU decomposition of A. There is some difference which is minus ED inverse F, and if D is, as D is A is a diagonally dominant matrix, if D is much larger, this is a small, the values of this matrix are smaller. So, we can get small error here, and we will say that this is not a complete LU decomposition, rather an incomplete LU decomposition of A. However, a preconditioner matrix can be evaluated from this and applied to solve the equations. So, the present LU decomposition as obtained by an SGS preconditioner is not a complete LU decomposition of a matrix. So, we can use SGS as a preconditioning technique, or symmetric Gauss-Seidel as a preconditioning technique for applying in conjugate gradient or GMRES type of solver. We can obtain the M inverse A steps as we are doing few SGS iteration steps on the equation system, and M inverse, if we have to find Z is equal to M inverse W, that also can be very easily found out, as M is of already in a LU or of LU shape. So, and this we saw that this is an incomplete LU factorization. In general, an ILU factorization process computes a sparse lower triangular matrix L. So, we will come to a general definition of ILU or incomplete LU factorization. In general, ILU factorization factorization process computes a sparse lower triangular matrix L and another sparse upper triangular matrix U for a general matrix A. Similar thing we obtained from the SGS preconditioning also. The exact form of lower triangular matrix and exact form of upper triangular matrix we obtained from a general sparse matrix A. So, that the residual R is equal to LU minus A, which is the residual that satisfies certain constants. One constant is that we might, because this is a sparse matrix, similarly R will also be a sparse matrix, and we might like to have 0 elements in some locations of our matrix, which will have certain advantage in storage of the matrix and certain advantage in applying the matrix. This is the general idea of incomplete LU factorization, that complete LU factorization is difficult. It needs to run Gauss elimination like steps for NQ operations. So, use some other method like a SGS preconditioning, or like first few steps of Gauss elimination you run and get few of the rows to be of LU form. So, some of these methods where an incomplete LU decomposition is obtained, and which will have a constant that some 0 elements are obtained in some of the locations. ILU preconditioning is obtained by running a small number of Gauss elimination steps on matrix A and then dropping few off diagonal terms to maintain the particular 0 pattern. So, what we said, like run few Gauss elimination steps and drop the few off diagonal terms to get particular 0 patterns, because we are not getting exactly LU decomposition of A, but we are getting two matrices which are of L and U pattern, and A minus LU can have some error, and that because exact LU is obtained, we do not need to do anything, the solution is obtained, M inverse A is equal to identity. When exact LU is not obtained, still M inverse A is close to an identity matrix in a sense that the condition number is very close to 1. So, that will also work, and that is the idea of ILU preconditioning. Run something like a Gauss elimination type of method and drop few of the off diagonal terms to get a particular 0 pattern in the residual matrix, and also to get LU form of the preconditioned matrix. And there are several methods like static ILU, which is basically running Gauss seidel for few stops, ILU IKJ, which is reordering the LU decomposition method, ILU 0, where there will be no extra digits added in the final LU matrix. A and LU will have almost similar sparsity, ILU P, ILU threshold, ILU crowd, different methods are there. And we can see from Yusuf Sir's book what is the effect of preconditioner what is the advantage when we apply preconditioner. GMRES is applied over 3 different matrices. One is finite difference 2D matrix, a finite difference over a 2D geometry matrix obtained from finite difference over the 2D geometry of pentadiagonal matrix, a septadiagonal matrix finite difference obtained over 3D geometry, and a ORS which is on an R structured geometry. In the first, when we do not apply any preconditioner, the matrix, this is a little larger matrix, 100 by 100 type of matrix. It took 95 iterations for the first case, where number of flops were 3841 kilo flops into 10 to the power 3 to get a residual of the order of 10 to the power minus 2 and error of 0.1. F3D, the other matrix, took 67 iteration, ORS took 205 iterations to get certain value of residual and error. We said that it is close to convergence, and the number of k flops is 3800, 11,862, 9200. When we apply SGS preconditioner from 95, the number of iteration reduces to 38. The kiloflops performance is almost half of that, while maintaining residue and error actually of almost of same order, little smaller here even with SGS. Similarly, for F3D the number of iteration from 67 goes to 20 to get similar order of convergence. From ORS from 205 it reduces to 110. So, almost half or more than half number of iterations are required, and also substantial improvement is obtained in terms of kiloflops. It does not exactly scale with the number of iterations, because some preconditioning steps, some SGS iterative steps are already added. So, it exactly does not scale like that, but higher a significant decrease in the computational over steps flops, and the number of iteration steps are improved. When you use ILU 0, the performance is further improved, especially from ORS from 110 it goes to 20. So, instead of the SGS, if you used Gauss elimination type of LU decomposition, the performance especially for ORS for the unstructured sparse mesh sparse matrix is improved. And if you use further improved ILU, which is ILU threshold pivoting, which was taking 205 steps in ORS, it now takes only 6 steps, and it was taking 9200 kiloflops, now it takes 341 flops. So, a huge improvement in performance can be obtained. So, preconditioning, if properly computed and properly applied over Krylov space based solvers, can give us extremely fast solvers. However, we have discussed some ideas about preconditioning, how the solvers are modified if preconditioners are obtained, and some very basic ideas how to obtain preconditioning. But the evaluation of preconditioners, especially ILU TP type of recently developed preconditioners, need more involved mathematics and some of the graph partitioning type of approach, that how you will keep the properties of LU at certain level, how will you minimize the residual, etc., which we have not discussed, but we tried to demonstrate that applying preconditioners can heavily improve the performance of a Krylov space solvers. And you can see that what was taking 95 iterations take 18 iteration, and what was taking 205 iterations for a very much sparser matrix takes only 6 iterations to solve. So, magnificent improvement in performance can be obtained if preconditioners can be applied properly, because the conditioning number of the solution matrix can be very well adjusted, so that it comes very close to 1, and in very less few number of steps we get the right solution. So, I tried to give you a brief overview of preconditioners, but it actually requires much more discussion, can be probably a module itself in a course can come as preconditioner, 2-3 weeks one can discuss over the preconditioners. But however, I think this gives one route to obtain very good performance of Krylov space based matrix solvers, or accelerate the matrix solvers to get to show great performance. One of the demonstration is through preconditioners. Thank you.